Hello, Lower 6. We're continuing today with circuit problems and we're going to have a look at parallel circuits. Remember last lesson we looked at series circuits and the rules that help us to work out what the potential difference is across components or what the current flowing through all of the components is. Series circuits in some respects are a little bit simpler than parallel circuits. With parallel circuits, first of all, you've got a lot more wiring. Okay, with a parallel circuit, each component is on its own separate loop. So the circuit I've built here, we've got a power pack, okay, which could of course be a cell. We've got 3 light bulbs. Each light bulb is connected on a separate loop. Okay, so the current doesn't go through each bulb in turn. It goes through this bulb separately, and then another branch it goes through this bulb separately, and then another branch it goes through this bulb separately. So it's not as easy to see just looking at this video image exactly how the wiring is set up. Of course, when you've got a circuit diagram, it makes a lot more sense. Now, as well as having the 3 light bulbs, I've also put a switch on each loop as well, which shows you one of the advantages of parallel circuits compared to series circuits. I can switch each one off and on completely independently of the others. Okay, whereas in a series circuit, all you can do is switch all of them on at once. Okay, we've got a slight wiring problem here, so let me just sort that out. Okay, there we go. They're all back on. Oh. I think it's this wire here actually, what's the problem? There we go. Okay, so all our bulbs are indeed switched on again. Okay, so that's a simple parallel circuit demonstrated for you there. Okay. Other advantages of parallel circuits compared to series circuits, well, you might be able to see this if I turn this light off here. Okay, it doesn't really affect the brightness of the other two, or at least it shouldn't do. Okay, it perhaps does slightly, but in the perfect parallel circuit where the wires don't have any resistance at all, you will have the same current flowing through each bulb, and the amount of current flowing through each bulb or each component will not depend at all on the number of components that are placed in parallel. So I could add another 10 bulbs in parallel here and they would all stay the same brightness. Okay, in reality that's not quite happening because I have got wires and connections that have got resistance. Okay, so you can see that this bulb is a little bit fainter than the other two, probably because of the bad connections and wires. Okay, but in a perfect parallel circuit you can add as many components as you want and you'll have the same current flowing through each one. Disadvantage though of parallel circuits is that as you increase the number of components in the circuit, you draw more current from the power pack. So I've got an ammeter here which is measuring the total amount of current coming out of the power pack. Now if I've got one bulb operating, I've got just over 1 amp flowing through that one bulb. 2 bulbs, that's over 2 amps flowing through. 3 bulbs, okay, I've now got 3.3 amps flowing, not through the bulbs, but out of the power pack. Okay, we'll come on to the current that flows through the bulbs in a minute. Okay, so that's an overview of what a parallel circuit looks like and an overview of what the advantages are of a parallel circuit compared to a series circuit. Okay, you can switch each one on and off independently. One bulb breaks, the other 2 will stay on. You can add as many bulbs as you want to the parallel circuit and they'll all, in theory, stay the same brightness. So what about the actual physics in terms of working out what are the potential differences and currents in a parallel circuit? Well, just like with the series circuit, there are rules, okay? And the rules are as follows. Okay, so I'm going to go through each one in turn. Rule number 1, it's Kirchoff's second law again. Okay, Kirchoff's second law, remember for a series circuit, the sum of the EMFs in any loop is the same as the sum of the potential differences in any loop. However, in the case of a parallel circuit, any loop, if we take this circuit here, any loop will only contain one bulb, okay, because you can't trace a circuit that has three bulbs, okay, even though three bulbs are connected, each bulb is on a separate loop connecting it to the power pack. So if I just take this bulb, for example, and I can trace my finger around a circuit that involves just this bulb, the sum of the EMFs will equal the sum of the potential differences. Now the only EMF in this circuit is from the power pack, so that is the sum of the EMFs is the EMF. So the EMF will equal the potential difference across the bulb. So whatever I set as the EMF on the power pack, I'll have the same potential difference, not just across this bulb, but across each of the bulbs. So rule number one for a parallel circuit, the potential difference across any two components that are in parallel with each other will be the same, okay? And if the parallel section is just connected to a power pack, it will equal the EMF of the power pack, okay? So rule number one, potential difference across any two components in parallel is going to be the same. And I'm going to prove that to you, because what I'm going to do is I'm going to switch each of these on. Let's hope they all come on again. Okay, and we're going to measure the potential difference across each one. Now, of course, it's not a perfect circuit because we've got resistance in the wires, but we should have, I would say, round about 6 volts across each one. I've got an EMF there of 6.6 volts. And of course, we've got some internal resistance in the power pack and resistance in the wires. But let me just try this. So I'm going to connect the voltmeter to bulb number one. Okay, 5.78 volts. I'm going to connect it to bulb number two. Okay. It is a little bit less, probably because of the bad connections. So we've got 5.2 volts. I imagine that the third one will probably be slightly less than 5 volts. Let me just try that. Okay, so the last one is a bit less, it's 4.7 volts. Okay, so we had 5.7, 5.2, 4.7. So it is going down because of the bad connections, unfortunately, in the circuit, and because of the wires having resistance. If they were perfect wires, perfect connections, then you'd have 5.7, 5.7, 5.7, and I could put another 20 bulbs in parallel, and they'd all have 5.7 volts across them, and they'd all be the same brightness as well. Okay, so that's the first rule, is potential difference. It's the same across each component in parallel. Okay, so potential difference, that's important to know. What about the current that's flowing through each component? Well, each component's got a resistance, and you'll get the full potential difference across each component. So if you did I equals V over R, you'll get the current through each one. Okay, and if I add another bulb on, it'll be the same current through the fourth bulb as there is through the third, the second and the first, because they've got the same potential difference across them, in theory. However, those currents will add up at junctions. So when these wires, first of all, the wire coming from the power pack will split up and go through each bulb in turn, and then the wires will come back together again and go back to the power pack. Now, at the junction, charge or current is conserved, which means that the current will split up into the current in each branch, and then it will join back together into the current that flows back to the power pack. This is called Kirchoff's first law. Okay, Kirchoff's second law was really conservation of energy. Kirchoff's first law is conservation of charge or current. And Kirchoff's first law basically says that the sum of the current flowing into a junction equals the sum of the currents flowing out of a junction. So it's telling you that the current splits up in a parallel circuit. So in fact it's almost opposite, well it is opposite to the rules in a series circuit. Remember, in a series circuit we had the potential difference being split up between the components, but the current being the same for everything. Well, in a parallel circuit it's the potential difference that's the same across everything, but it's the current that gets divided up, that gets split up. Okay, so the current at a junction adds together. If you've got 3 wires flowing into 1 wire at a junction, you'll add the currents together. Now I can show you this by showing you what the current's reading on this ammeter. I could put the ammeter on each separate loop, but what I've got here is the ammeter on all of the loops combined when it flows back to the power pack. At the moment it's reading 3.2 amps, but if I turn off one of the bulbs, it goes down to 2 amps. If I turn off the other bulb, it goes down to 1 amp. Okay, as I was saying before. So that's the rule for current then. Okay, current stays, current splits up, in this case 3 ways, as the current goes through each loop in turn, and then it joins back together again. So you've got rules there for the potential difference, you've got rules for the current. What about the resistance? Okay, well, before we think about the mathematics of resistance, okay, we might want to know what is the combined resistance of all 3 of these light bulbs compared to just 1 light bulb. Now, if we were joining these in series, as we added more light bulbs, the resistance would go up. Okay, we discussed that before. If you have 2 resistors, R1 and R2 in series, the combined effective resistance of the 2 of them would be R1 plus R2. Okay, it doesn't work like this in parallel, because if you add more bulbs, you're giving more routes for the current to take, and indeed the total current going through the circuit will go up. The potential difference across the whole section stays the same. Okay, 6 volts, that will stay the same, but if you add more and more components, the current actually goes up, which means that the effective resistance goes down. So in parallel, when you add resistances, the resistance drops, it doesn't go up. Okay, now there's a formula which will let you work out what the effective combined resistance of a set of resistors in parallel is. And the derivation of this formula I'll explain on the notes that I give you. It's not an easy one to sort of explain verbally, but it's basically, it comes from the 2 rules that I just said about potential difference and current in a parallel circuit. And the equation is 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3 plus so on. Okay, so that's how you combine a load of resistors that are in parallel. So imagine that these 3 light bulbs were each 30 ohms. Okay, each one of them was identical and that each of them were 30 ohms. If we use that formula, we'd get 1 over 30 plus 1 over 30 plus 1 over 30, which is 3 over 30, and that would equal 1 over R. So R would equal 30 divided by 3, which would equal 10. So if we had 3 identical resistors in parallel, the total resistance would be 1/3 of the resistance of a single resistor. Makes sense, because you're giving 3 times as many routes that the current could take, and the current goes up 3 times for the same potential difference. So that's why the resistance would drop to 1/3 of its value. Obviously, if we had a 4th identical resistor, the total resistance would be 1/4 of the resistance of an individual resistor. So that's how we do calculations, folks, in parallel circuits. Okay, potential difference is the same across everything. Current splits up and rejoins at junctions, so that's Kirchoff's second and first laws. And then you can derive this formula to work out the effective combined resistance of a load of components in parallel. 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3 plus ad infinitum. So that's it. That's parallel circuits in a nutshell. Okay. and you will be expected to do sort of circuit problems that involve parallel sections, parallel components. You may also get circuit problems that involve a combination of series and parallel components. Now, this can be a little bit tricky. What you've got to do is sort of separate them out. Okay, so for instance, if you've got two series components and one parallel, so imagine you've got these two resistors, and let's say they're in parallel with one light bulb. What you'd have to do is you'd have to add the two that are in series together. So you'd add these two resistances, and then you'd use the parallel formula to work out the total resistance with these two and that one. Okay, and remember, you'd get the same potential difference across this one bulb as across both of these in series, and these two would split that potential difference because they're in series. So you may get circuits where you've got a combination to deal with of series and parallel components, and you have to basically add any two in series where there's no branches between them. You would add them together. Then you would sort out any parallel sections, okay, and work out the total resistance of any parallel sections. And then if you've got anything in series with the parallel sections, you would add that on at the end separately. And that's how you'd work out a total resistance in a combination circuit. Okay, that's it, folks. We'll give you a problem sheet, we'll give you some notes, and we are trying to do this fairly quickly because there is one more lesson I want to do before the end of term, which will be on internal resistance. So I want you to try and have a go at this by Tuesday evening, please. Okay, thank you very much, and enjoy your evening.